Alrighty, what we're going to talk about in this is electrolytes. Electrolytes are an important thing for us to pay attention to. You've probably heard this somewhere, right? We talk about sports drinks that have electrolytes in them, things that are good for you. Electrolytes are crucial for human and animal anything function, right? They're required for nerve impulses and muscle contractions and all this fun stuff. So what this video is going to let us get into is what are electrolytes? How do we classify things? How do electrolytes work? And then we're going to start using this idea to do reactions and predict stuff. Okay, so let's talk electrolytes. Electrolytes would be a substance that dissolves in water to make a solution that conducts electricity. So to be an electrolyte, it's got to be soluble in water. That's our main criteria. It's got to be soluble in water. Um, and the solution that's generated has to conduct electricity. That's why it's called an electrolyte. So if we look here, um, let me get this other definition out of the way. A non-electrolyte will dissolve in water and make a solution that does not conduct electricity. Okay, so here, if we just have pure water does not conduct electricity. This color does not work for me. Um, Pure water does not conduct electricity, and the light bulb doesn't light up. Okay, these guys are electrolytes, and the light bulbs light up because we have ions in solution. There's positive ions, negative ions in the solution that help conduct the electricity, and the light bulb lights up. Okay, if it is not soluble, it is not an electrolyte or a non-electrolyte. We say that is insoluble. Okay, so our baseline criteria is going to be that it has to be soluble in water for us to even consider it being an electrolyte or a non-electrolyte. Okay. What's next? Okay. So when we're thinking about electrolytes, we're going to think about hydration equations. We'll come back to this and talk about hydration in a little bit more detail later on too. Um, Non-electrolytes dissolve in water, but do not dissociate into ions in solution. And this will be most things that are soluble molecular compounds, things like sucrose, C12H22O11, solid, dissolves in water, right? This is just sugar, okay? Dissolves in water and becomes aqueous, but does not dissociate into ions. Remember, you have to have ions in solution to get the current to flow to light the light bulb. So you're not going to get anything happening if you don't have ions. There it is. Okay. Electrolytes, on the other hand, will dissociate into ions in solution. So this is all soluble ionic compounds are electrolytes. So we can say sodium chloride, which is a solid, will dissolve in water and dissociate into sodium ions that are aqueous and chloride ions that are aqueous. Okay. There are also some soluble molecular compounds that act as electrolytes, and we're going to look at those too as we're talking about this. Okay. So our big thing here is non-electrolytes don't make ions, electrolytes do. And this is all when they're soluble in water. Okay. Um, those molecular compounds that are electrolytes can be classified as either acids or bases. And we're going to come at this from the Arrhenius definition. This is Svante Arrhenius. He got the Nobel Prize in 1903. He's done a lot of stuff, but mainly it's the acids and bases that we're concerned about here. Acids dissolve in water and produce hydronium ions. We talked about hydronium ions already. This will be things like HCl. HCl is a gas, will dissolve in water, which is a liquid, to give us H3O plus and OH minus. Okay. Remember, you can think of this as H plus, not OH minus. What the hell am I talking about? This is Cl minus. Okay. Forget that happened. Right. We could write this in terms of protons instead. HCl dissolves in water to make H plus and Cl minus. Okay. That works. Bases dissolve in water to make hydroxide. That's where the hydroxide came from. Okay, so bases, um, well, are say something like sodium hydroxide. We're going to get into this. It's a solid, dissolves in water. We're going to get sodium ions, and we're going to get hydroxide ions. Okay, that works quite well. Okay, um, yeah. So that's one thing. We're going to also note that not all electrolytes are equal. Some are strong and some are weak. And we can look at, if we go back and look at this, notice this light bulb lights up much brighter than this one did. So we can classify this as strong and this is weak. And the real definition here between strong and weak is relative to how many ions you get in solution. Okay. Your strong electrolytes dissolve in water and completely dissociate into ions, right? This is all soluble ionic compounds. So if we decide that a molecule, that an ionic compound is solid, it'll dissociate into ions in solution. This would be like our sodium chloride example, but maybe we could do it with KBr as well. Also soluble, dissolves in water, gives us a K plus and a Br minus. Okay. Um, it dissociates completely. That's why we use this arrow, right? Our good reaction arrow that points in one direction. Our other things, the molecules that dissociate completely, they could be strong acids. Strong acids dissociate completely. Now, there's a lot of things that act as acids, and we named a lot of these things before. Remember, we're going to start with H. Okay, this yellow is not going to do it for me again. Um, strong acids are something that starts with H and has something else next to it. Okay. Remember, they only act as acids when they're aqueous. Okay. They'll dissociate, give us H plus, that is aqueous, and whatever the anion is, that is aqueous. Okay. There are tons of things that do this. Only 7 of them can we consider to be strong, and we have to know these so we can pick them out. They are hydrochloric, hydrobromic, hydroiodic, nitric, chloric, perchloric, and sulfuric. I made a little note here. Remember, sulfuric has 2 ionizable hydrogens, H2SO4. Only the first is strong. Right? The second is weak, and we'll come back to that more in Gen Chem 2 when we talk about uh, acids in a lot more detail. Okay, so we have to know these 7 acids. Notice they all dissociate completely, so their equation just goes to the right. Okay, weak electrolytes do not dissociate completely. Okay, so they're going to exist as both ions and molecules in solution. Okay, so we can classify our weak electrolytes as either being weak acids or weak bases. Our weak acids are anything that is not one of the 7 strong ones that we see here. Okay, but if we know it's an acid like acetic acid, HC2H3O2, acetic acid is not one of the strong acids. So we can say acetic acid is a weak electrolyte and it dissociates not completely. In actuality, only roughly 4% of acetic acid is dissociated. Okay, but we do get some ions in solution, so the light bulb does not light up completely. Um, the other thing we'll notice here is, oh, you know, one of these days I'll learn how to control PowerPoint correctly. Um, one thing we notice here is that we're not using our forward arrow. We're using this equilibrium arrow. Okay, it's a reaction arrow that goes in both directions. This is telling us that this reaction is reversible, right? that the forwards works and the backwards works. So really we can say this is acetic acid will dissociate to give us H plus and acetate, but we can also read it as to say acetate and H plus will come together to reform acetic acid. Okay. And as you can see this, all of the things in the equation are going to be present in the mixture at the same time. We also refer to this as a dynamic equilibrium. Because the forward and the reverse reaction are happening all the time. Okay. Just so happens these things are weak electrolytes because the forward reaction doesn't happen very much. It happens enough that we can see it, but it doesn't happen enough that it's continuously just ions in solution. Okay. We can also have weak bases. Weak bases behave like ammonia. Remember, ammonia is NH3, and all of our weak bases are going to behave like ammonia. I don't want to say aqueous. Let's say gas. Okay. Ammonia is a gas that, and this acts as a base because it reacts with water. And when it does that, it makes the ammonium NH4 plus and generates a hydroxide. So this is a base because we've generated hydroxide. Okay. This is also reversible. This is weak. Okay. In actuality, the reverse process dominates. There's very little OH minus in the solution, but there's enough that we can measure it and we can see how it goes. Okay. For us, all weak bases are like ammonia. Okay. They have some sort of nitrogen. Maybe they got a bunch of organic crap around them as well. Okay. But that nitrogen is going to pick up a hydrogen from the water and make OH minus, and that's why it's going to work. So for example, if we had pyridine, which is C5H5N, this is going to do the same thing. And if we can dissolve this in water, it'll react with the water and give us the pyridinium. You don't have to know these names. It's just easier to say it. NH plus aqueous and give us OH. Come on, dude. OH minus. There we go. Again, we made OH minus, so this is acting as a base. Okay, and we will dive into this in a lot more detail in Gen Chem 2, but I just wanted us to know it that all of our weak bases are organic things that look like ammonia. Okay, for reference, right? You may be thinking, well, we talked about strong acids and weak bases, and we talked about weak bases. What about strong bases? Our strong bases, strong bases are soluble ionic hydroxides. Okay, and that makes them strong. Okay, strong bases are soluble ionic hydroxide, right? So sodium hydroxide is one of these, potassium hydroxide. There's several of these, and we'll talk about them again later too. But you don't have to stress too very much about strong bases because they behave the same way as soluble ionic compounds. Okay, all right. Let's look at this. We have to be able to classify things based on their status as an electrolyte. Okay, keep in mind that whatever you're classifying must be soluble in water. If it's not soluble, it's not going to be an electrolyte. Okay, so if it's soluble and if it's ionic, it's a strong electrolyte by default. That's just how it goes. All the ionic compounds that are soluble dissociate completely into ions in solution, and that makes it a strong electrolyte. Okay, if it's a molecule, we have to go back and ask ourselves, is this an acid, a base, or neither an acid nor a base? If it's neither, it's a non-electrolyte because it's not going to make ions in solution. If it's a base, it has to be a weak electrolyte. Remember, these are typically things that have nitrogen in them and some other stuff attached to them. Okay, if it's an acid, well, it could be strong or weak, and it just depends. Okay. Is it one of the seven strong acids that we have to memorize? Yes, then it's strong. No, then it's weak. Okay. Strong electrolytes are strong acids, strong bases, ionic compounds. Weak electrolytes are molecules that are either weak acids or weak bases. Okay. Hopefully we can get this straight. We'll practice, 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 and work through it. Um, and hopefully the weak electrolytes won't kick us in the butt. Okay. If you have any questions or need anything, just let me know. I'm here. Have a good one.